So today, I appreciate your time. No, you have other sessions you could be in. Thanks for choosing this one. Today, I'm going to talk about centralized versus distributed AV and control processing. My name is Ben Olswang. I am VP of Engineering and Product Development at Symmetrix. I've been with Symmetrix about 6 years now. Before that, I was at EAW and Mackie, Loud Audio, doing product management and engineering. I was there for 18 years before that. So I've been in the industry for quite a while, and quite honestly, I joined Symmetrix for the chance to work on this concept that we're going to be talking about today. For those who aren't familiar with Symmetrix, I'll do the really short history just to kind of understand where we're coming from a background for this talk. Symmetrix was founded in 1976 by Dane Butcher. He was a recording engineer in LA at the time, working on, in the studio, working on producing albums. And back then, when you needed a piece of gear or needed to fix something, you kind of had to do it yourself. And so he started tinkering, adding, and eventually started his own company making custom studio equipment. And Symmetrix was born. Symmetrix started off making more and more studio gear. We changed into more broadcast-focused products. The one with the colorful buttons had a bunch of different versions of that used in radio in particular. There's a dump button on there for when everyone swore, and that was just across pretty much every radio station in the 80s and 90s particularly. And then in the early thousands, Symmetrix started in on commercial audio. We had one of the first digital commercial audio processors in the 322, and we continued to grow and expand. We were one of the first adopters of Dante. In more recently, we've been adding control to that space so we could provide a whole cohesive system with AV and control. And so, Symmetrix, as an engineering principle, we're all about innovation and engineering precision-crafted products. And we really want to be thinking about new ways to solve problems and not solving them in the same way as everyone else. And so about 5 years ago, about 7 years ago, we had new ownership. We're still a family-owned company. We definitely pride ourselves on that. You can call us up and you get a real person. But our ownership really pushed us to rethink what audio-video processing and control processing means moving into the future. And that's really what we've been working on the last 5 years. And today I'm going to talk to you about the general concepts and problems we were trying to address and how we think those can be solved. And so if we think about most AV and control systems today, they generally follow a centralized processing model. And I'll define that in just a sec, but just the overview of today, we're going to talk about centralized processing, why that has become the model, what its pros and cons are, and then a new approach using distributed and scalable processing and what we feel are the benefits to that. And hopefully at the end of the talk today, you can think about your systems, your applications, and think about where you want to take those into the future and what's best for you. So to define, make sure we're all on the same page, centralized processing, the way we think of that is you have a single processor that is doing all of the processing, and all communications, audio over IP, video over IP, is all kind of going in and out of that centralized processing unit. And different manufacturers call it different things, an engine, a core, a DSP, but it's all the same concept. So I'm definitely not picking on any particular manufacturer. I'm really talking about ourselves as well, our previous architecture, and what we see as the future. So this is centralized processing, and we'll talk more about that in detail. But distributed processing at a high level, we see that as all of the participating products are doing some of the processing or have the capability to do some of the processing. and all participating products communicate and route AV over IP directly between one another. And so there's much more awareness of the rest of the products in the system. And so at a high level, this is what we're talking about. And we identified some major problems that we wanted to focus on and improve with centralized processing. So one, and we're going to go through each of these in more detail. First one, though, really has to do with scalability, where you can scale a system with low cost, or you can scale a system with low complexity, but it's really hard to do both, and we'll talk about that. Architectural fragility. You end up with a single point of failure. The more rooms that are dependent on that single processor, the more that single processor can take down an entire system if there are problems. Update risk and inefficiency. If you want to update one room, make changes in a particular room, if everything is dependent on that one processor, you can have some unintended consequences, or at the bare minimum, you have to do it after hours because you don't want to risk issues in the rest of the facility. Forced obsolescence. Because everything's on one processor, if you need to upgrade that, you're not adding to your system. You're doing a lot more replacement than adding. And that's another problem we wanted to address. And finally, all those together really point us to increasing the overall cost of support, upfront cost of product, and cost of maintenance over time. Your team's cost, people cost. So let's talk about each of these, and I'll give some examples about each of these. So, unnatural scalability. As I was saying, you can have low cost or low cost or low complexity, but never both. So this kind of example spaces, I'm going to use this kind of look and feel a lot as we go through. So just to give us a tour, I'm generally showing examples with 3 rooms because that's more than 2. Fits on a slide nicely, but think of it as lots of rooms. And in the most direct way to do it, you would implement each room with its own processor and its own control. The screen there is just representing control in general, and the I/O is shown there as XLR wall plate. It's just representing I/O in general. That could be a ceiling mic, that could be amplifiers. It just fits nicely there on the slide. So rooms have control, processing, and I/O. And the most direct way to do that is an isolated view, and you can do this with any product out there today where you handle each room separately. But I think we all know that you often have higher costs when you're approaching that, because if you're having a DSP or a control processor in every single room, there's kind of a floor of what that processor is going to cost, and you end up having a higher cost to implement that. It does make things simple to handle each room independently. And so we often see this, or probably most often, where you have a larger processor that's handling multiple rooms. And again, it doesn't mean that the entire floor is on one processor. It could be, entire building could be on one processor nowadays with servers. We make a server that does 384 by 384, and you can handle the whole building on that. And there are really big cost benefits to doing that, as opposed to having a processor in each room. But you end up with complex designs and some of these additional problems that I mentioned. So what we see most is this, or at least this centralized model in many different spaces. So let's talk a little bit more about some of those problems. Single point of failure. This one's pretty obvious. If there's a problem with that core, rest of your system goes down. Every single one of those rooms is done. So we don't like that. Update risk. So let's say there's a problem or a change that needs to be done in that second room. Well, very often, if you want to address that with a centralized processor, you have to push updates, and because the whole system is interconnected and tied to that same design, you're bringing down all of those rooms every time you push an update to fix one room. So what ends up happening is you do it after hours, you have to plan to do it first thing in the morning or last thing at night. It's never the convenient time when a problem arises or when staff is on site, and then you're pressed for time, have to get it done before the next issue, or before the next class is happening in room 1 and 3. They're not having any problem, but I had to take them down in order to address the problem in room number 2, and now everything's back online. Another problem we saw was this concept of having to replace products as opposed to adding products when you wish to expand. So with 3 rooms, that little bar I've added to the bottom is representing processing capacity in your DSP. So again, you probably have more than 3 rooms capacity on a single DSP, but just using that as an example. So let's say 3 rooms fits fine on this, and then the upgrade cycle, maybe you plan everything, every year you're upgrading another room in a particular building to get through every space in 10 years or whatnot, and so you want to upgrade another room. Well, at some point you'll hit the capacity of the device that you already have there, and what do you have to do? Well, you have to either re-architect everything or replace that processor with a much bigger processor, a bigger server that costs more. So you're doing a replacement rather than an addition, and we see that as a problem as well that we wanted to address. And so all of these things ultimately lead to increased cost. Again, up front, but not to be ignored is the cost of your time, your team's time. And so this was an area in particular that we've been thinking a lot about, and that we wanted to create a new way of building systems that inherently in its architecture addresses some of these key problems. And the solution we decided on and have implemented, and I'll be telling you more, is a distributed and scalable model. And our solution is called Cognio. And this isn't a talk about Cognio specifically, and so I'm not going to tell you very much about all of the cool things that we think Cognio can do. This is about one area of it. We're downstairs at the table, and we'd love to talk about lots of other aspects of Cognio after, but today we're going to focus on the distributed and scalable benefits of Cognio. So, one of the key aspects is that Cognio, every product is smart. Every product has processing. And that, if we think back to that distributed slide, I probably should have inserted it here to remind us, that's the core aspect of the distributed processing, is that every product that participates in it has processing and contributes to the overall capacity of the system. And that leads to a bunch of benefits that we'll talk through. Reduce cost, and reducing complexity. Those two things that we said in a centralized model are really at odds with one another. You get to treat large systems as smaller, independent spaces. It's inherently more fault tolerant through isolation. It allows you to share processing from a single space across multiple devices, and you can update spaces without affecting others. It's much easier to upgrade when more is needed, and in the end, you end up with less hardware, and less hardware is going to mean lower cost overall. So we're going to talk through these in detail, but to get there, I just need to tell you a little bit more about the architecture and how it's implemented under the hood. So our architecture changes kind of one core concept. Again, looking at pretty much every platform out there nowadays, it could be split up in this view, where you have processors that are doing all of the hard work. They're the smart things. And again, this could be a DSP, this could be a core, this could be an engine, whatever brand uses for that term. And you have these simple endpoints. And I'm using the word simple to mean they don't do much on their own. So an I/O, Bluetooth I/O, XLR I/O, without a processor behind it to do the routing, to do the audio processing, it doesn't do a lot. Control screen, wall remote doesn't do much unless there's a control engine behind it communicating with everything else. And so you have these smart products and these simple endpoints. And in a distributed system, all products are smart. Distributed processing is available on all of the devices that are participating in the system. So in our case, all of the Cognio products. And so looking at this another way, how we're implementing this is every single product in the distributed platform is running the same operating system and firmware. And that means every single product, endpoints, touchscreens, and traditional looking DSPs are smart and have the capacity to have the same feature set as all other products in the platform. The only difference is the physical I/O and nature of the product. And so if we look at that Cognio operating system bundle, we see that all products have the same features. They all have audio processing. They all have control processing. So in Cognio in particular, audio processing means open architecture DSP, up to 96K, software Dante, AEC, paging, playback and recording, and they all have control processing. They all have a web server, so you can control it from any device. They have automation, control drivers, Lewis scripting. Every product has these. And the way we've achieved that is going from a traditional chip-based platform where every feature is associated with a hardware chip to a general purpose platform where every product has an Intel x86 chip or an ARM processor in them, and it's those chips that are running that Cognio operating system. So again, that touchscreens in the Cognio product line have DSP and control processing in them. Cognio endpoints have a small amount of processing in them. And so the only difference is not the feature set, it's how much of each feature is available in a particular product. And so this is attempting to illustrate that. The big circle is representing a large processor. So this could be an Intel Xeon in a server that has a large capacity for processing. And then the smaller circle is representing a smaller product with a smaller processor, like our touchscreen, and it has a smaller overall amount of processing. And so the large product, you can see within the processor, we've subdivided how much processing is allocated to each feature independently. So the large one has a whole lot of signal processing, while the other one is more evenly distributed amongst features. And so this is kind of core to the concept that every product has all these features. It's just different amounts of each feature, and you're simply choosing how much of capabilities you need. So let's take all that platform concept and start talking about real systems and how they can be deployed differently. So the simplest one is a small room. Again, coming back to the centralized model, you have a processor in the middle, and it has control and audio transport between all of the other devices. Again, I/O, video camera control, the different device types, where when we look at it in a distributed model, you don't actually need a processor. What you need is processing. And so as long as a product in that room is doing the processing, it can be done with a product that's already there. So in this example, we've removed the need for a dedicated processor, and we're doing the processing, in this example, on that screen. And the chips today are amazing, and the chips already built into our touchscreens have enough capacity for 16 by 16 channels at Dante, enough open architecture processing for EQs and compressors and gates to go along with that. There's enough for a couple channels of AAC, so you can do a small room and do this size room on a touchscreen. Got 4 mics set up in an analog mixer. I could have a touchscreen on a wall that could easily do this entire room. So this allows you to scale and use less product, less hardware to achieve the same goal. And the way this scales, because every room is being done with its own processing, it scales really nicely. But if you do need more processing in a particular room, so again, like this, if they want to handle 20 mics in a room like this, our touchscreen only does 16, for example, that can be scaled, but instead of replacing the processor that's there with one that has higher capacity, you simply add to the system. And you get to choose what you add based on your needs. Do you need more control? Do you need more I/O? As long as it gives you the feature set you need, you would have multiple paths to solving it. And you're adding to it. So in addition to giving them more processing, you get a second touchscreen in the room. So the users now are getting tangible features that they can feel, as opposed to a larger black box in a closet. Okay, so let's take that and look at those additional, go back and look at those problems that I talked about earlier and see how they're solved in a distributed model. So scalability, unnatural scalability gets handled by being able to treat large systems as smaller independent spaces. So this is the view we talked about before. We have a single processor handling each of those rooms. And if I still want to stay in the current architecture, I could do that, as we showed before, keeping each one with its own dedicated processor, but we talked about how that adds a lot of cost to the system. Well, in a distributed model, assuming each of those rooms could be handled by the screen that's already there, any room that can be, you can get rid of that processor, and you can see as you start to scale to more and more rooms, the savings really starts to add up. And you can mix and match. It doesn't mean that every room has to be done this way. If you need a dedicated processor because one particular room needs a very large amount of capability, like the ballroom downstairs, you'd handle that in a more traditional sense with a dedicated DSP-shaped DSP, I like to say. But you get that flexibility. Now, the key is you want to be able to handle these spaces from a single view in your software. And again, we're not going into detail on how we solve this in Cognio, but just a single screenshot shows us that I have my view of my site, and each of those big boxes represent the different spaces in my site, the different rooms. And we can go in and edit each one independently, but they are all contained in one site file that has access to pass control between spaces, audio and video between spaces. Architectural fragility. With distributed systems, they're just inherently more fault tolerant. We showed this slide before. If there's a problem with that core, the entire set of rooms that it's processing is taken down. Well, this one's pretty obvious. In a distributed model, if there's a problem with room number 2, room numbers 1 and 3, they have no issues. They're up and running. They're still chugging along just like nothing else happened. So you get that isolation when needed. But this can also be translated to update efficiencies, being able to update each space independently from one another. So again, this one's pretty obvious. If I want to make changes to room number 2, I can just take down room number 2, push updates. Room numbers 1 and 3 are still running without any issues. Now, that one's pretty obvious and pretty simple, but because we have a distributed system from the beginning, we've accounted for that both in the individual processors and also within a single processor. So you get the benefits with a single processor. Let me show you that. So in this case, if I'm having a problem with room number 2, in Cognio and in a distributed nature, each one of those rooms is actually implemented on the single processor as a separate entity and completely independent from a push and pull synchronization standpoint. So in Cognio, if there is a problem in room number 2, I can push updates to that room without taking down room number 1 and room number 3, even if they are on a shared processor. because it was designed for that distributed architecture from the beginning. And that, I can't tell you, is really a key benefit that all of our early adopters are appreciating. And we also see this with improving the forced obsolescence story, because you can upgrade by adding distributed devices and not replacing. So again, if we run into a limit, we want to add a fourth room. In a traditional centralized system, I only can have one core, so I have to replace that core with a bigger one. And with Cognio, again, you have more flexibility. So if it's fully distributed with processing in each space, I can just add another room. And again, I don't need a dedicated processor for that space. But even if I have shared processing and adding another room takes me over the budget, because it's distributed, I don't have to replace the processor. I can simply add a second processor, but they will act as one, covering all of those spaces. They're sharing their capacity in the background that you don't have to pay attention to. So again, you can simply upgrade instead of a very large upfront cost to upgrade, it's a much smaller addition to your system. That scalability is always much more predictable as you add room to room. And finally, let's just look at a bigger system and show you just how much hardware can be removed in a distributed system. So we've been talking about 3 rooms and 4 rooms. I'm going a little crazy now, and I got a picture with 5 rooms in it. So in this relatively straightforward kind of, elementary school example, it's one of the easiest to represent. You'd have an office, a gym, many classrooms, more than 3. But in general, in these environments, you're handling this with a single server in a rack closet somewhere. And this has been the most economical way to approach it, because each of those rooms, the requirements for each room is actually really simple, right? What's happening in an individual classroom? Not a lot. And so that it makes sense to centralize everything in an equipment rack. But that server is very expensive, and you have a very high amount of network traffic going on, because every single classroom is having to send all of its signals back to that equipment rack where it's being processed and then distributed back out. So you have a very high network load and a very, what's the right word? The system is very dependent on that network switch to make sure everything is going where it needs to be. If you have a switch failure at that equipment rack, that's just as bad as a DSP failure in that equipment rack. So if we look at it in a distributed way, we can take a glance and say, hey, every single one of these rooms has control already. It already has an opportunity to do distributed processing. So why not just use the processing that's already there in my touchscreen and use that to do those rooms? We talked about how simple the processing needs in a particular room are. That allows you to do that. And in the ideal case, you could completely remove the need for a centralized equipment rack with a centralized switch and a centralized server, and just make everything distributed. And you can mix and match. Again, this is the idealized case, but it shows you just how much cost can be removed by designing for distributed from the beginning and planning for that. And I have a bonus benefit that I haven't talked about yet. Distributed processing inherently lets us do more offline, and one of those benefits is offline emulation. So let me explain how distributed gives this. So we saw this slide before where every single product is running that same firmware operating system, we call it, but the same firmware capability, that every product has all of the same capabilities. Well, not only do the hardware products have that, but in a fully distributed system, the design software that you're using on your laptop also has those same firmware capabilities. That exact same firmware file is available in the design software. And that means that you can emulate the full system in advance before you have any hardware. So I have a video here just to keep things simple. So this is a view of a pretty straightforward design. I have 8 inputs, 6 outputs, a matrix mixer in the middle, some processing between. And let me just play that video and show you how the emulation works. So I'm offline, I have no hardware, and we have a mode called operation mode. And in that mode, I can insert a signal generator. It's probably hard to see, but I have a signal generator at the bottom that I've enabled. And now I can click on a node on each module, and it inserts the signal generator right on that module. And you see the little green bars, those are meters, they're flashing. And I can see that audio is going into that matrix, but it's not going out of that matrix. And this is real live audio being processed on my machine. Effectively, it's like a DAW in the background on my computer. So I can go into that matrix and go, oh, well, I haven't patched anything, duh. I'm gonna click and patch those. And you'll notice as I patch those on the output legs, I start to see those meters appear. And so I can do a full line check offline on my laptop of an entire room, an entire building, a day, a month, a year before hardware arrives or the install happens. So you have the ability to completely prove out your system, tweak your design, and improve it, making more, allowing you to do more offline when it's cheap at your desk, and saving cost when you have lots of people dependent in the room and you're doing your installation during commissioning phase. So that's just one of the additional features that a distributed platform gives us. Oops, it's playing again. So, in summary, I'm just going to kind of go through the benefits again. Because all products are smart and have this processing, it can reduce overall cost and reduce complexity of your system. And inherently, the core concept is you get to treat these big spaces as separate individual spaces that are independent, whether or not they're run on the same product or not. It decouples the where the processing is happening for how you want to architect your spaces. It's inherently more fault tolerant, allowing you to share processing on a single device across multiple spaces, and you can update spaces independently from one another. It's easier to upgrade and ultimately gives you less hardware and a lower cost. There's actually one more big benefit that we see, and that's a benefit to you, allowing you to have way more options to solve your problems. You can take a distributed system and treat it exactly like you're always doing, but you can mix and match and use some of these distributed concepts to give you the features and benefits that you need. So really it lets you solve your problems in ways like you could never do that before. So that's all I have. I think we have a little bit of time, yeah, for questions. So if there's any questions, I'm happy to answer them. Yeah. Yeah.
Is that part of the control process?
Not inherently by the system. So having to separate the conceptual aspect of distributed processing for what is implemented right now in our particular deployment, right? So conceptually, no. The architecture allows us to have not only primary aspects of control, but secondary and failover. Because everything is running the same firmware, everything has the same capabilities, you can assign backups and failovers just like you might already do. So if you want to over-provision a room and say, I'm going to have an extra touchscreen, but I only need processing from one to do the room, you could assign that level of failover. We have not, full disclosure, implemented that feature yet in the shipping code, but the capacity at an architecture level is designed to do such a thing. Does that answer your question? Okay. Yeah.
How does it play with others? Like if we got a few rooms set up with your system,
yep.
And then in the rest of the building we have like a more traditional system. Is there any way to integrate them?
Yeah, absolutely. Yeah, again, just trying to be really explicit, speaking for general symmetrics. So speaking for symmetrics now, so one of Symmetrix's goal is to be the best at integration, right? We are not a company that provides everything in a vertical statement. You're not going to buy every camera and mic and speaker from Symmetrix. We inherently are focused on making sure we play well with everyone, and Cognio is no different. So in its distributed nature, though, it actually plays better with everyone, even better. So one, we use Dante general. You can route Dante, mix and match that the same. But from a control standpoint, because every single product is a true control processor, that means it can be used to control anything, and or it can be controlled by anything. And so both are open control APIs. You can write scripts in Lua to control other things, or just use our API to be controlled by something else. So that means that all products integrate really well and really consistently. So this concept of scalability transfers in our mind to having to be able to learn things once and never and be able to deploy that all across the board. So however you're used to doing control, once you learn it for one Cognio device, they all work the same. So we're really into open protocols and open APIs for control and audio and video transport because we see that as our one of our core benefits, because we're not a company that wants to sell you one of everything. And if you want to talk more, we can go into the nitty-gritty details of our control API and whatnot. Any other questions? Yeah.
So in a cost comparison, I understand and appreciate the benefits of this type of system.
Yep.
We're looking at sort of an apples-to-apples type of comparison. What are we looking at for future costs?
Yeah. In our case, so again, some metrics in general, some of our core beliefs are about audio quality and craft build. So all of our products have this as a kind of centralized tenet. So even generally right now, you might see a little bit of a premium on a Symmetrix endpoint over a non-Symmetrix endpoint because we really focus on that quality. We're known for that. But inherently in distributed audio, what it does is increase the floor maybe a little bit, but the amount of processing that any processor out there can do has really diminished that. So as I was saying, the chips that are in our touchscreens already can do all of the things we wanted them to do. So we didn't have to upgrade our touchscreens to support distributed processing. We did choose to because we wanted to increase their capacity even more. So we went kind of one notch up on the processor inside to a slightly larger ARM processor, but we didn't have to do that. That was a kind of strategic choice versus an architectural choice. So you do have a little bit of a potential to increase the floor a little bit from an architecture standpoint because you have this minimum capacity that your chip needs to be able to do. But once you reach that point, then it's more of a strategic choice by the manufacturer, us, of what chip do we want to put in this product and where we want it to sit. In general, it's pretty close. It's just maybe a little bit more of a premium, but that would be more strategic than a architectural reason. And again, speaking for Symmetrix, I don't think we've deployed it right yet, but we do have a kind of cost comparison calculator that's being built and will be on our website pretty soon. So you can kind of put in, all right, I want to build a system this way and build a system this way. What does it look like for my particular application? And that'll be on our website soon. Great. Well, if there's any other questions, feel free to come up afterwards and come down to the booth, or the table, excuse me, not the booth. And there's myself and Don in the back. You want to just raise your hand just so people know him. He's also with Symmetrix, and the guy Stu down there. Made it simple, Don, Ben, Stu, single word names, single syllable names. So we're happy to talk more about anything Symmetrix while you're here. Appreciate your time. Thank you.